Alright, now that we have a giant word list, and last 2 weeks we talked about the lazy sequences and recursion, let's put all these together to solve a classic and interesting problem of word squares. So here in the Wikipedia page depicted the oldest and the most famous one, Sator Arepotenet Opera Rotas. Here is a more modern one illustrating what is going on. So we build up a square of letters that every row and every vertical column is a legal word from the dictionary. Now here, these old-timey squares that then we can easily restrict our search algorithm to look for. You notice that the words in the horizontally and vertically, they're always the same. So heart, the first row and the first column is also heart. Now we're gonna make this problem more interesting by saying that every word has to be different, so you cannot reuse the same word in any row or in column. So then the search problem becomes more difficult, but then also more satisfying. But even so we have to be really careful, because the exhaustive search for all the combinations. So suppose you have 10,000 words available. So the first you have 10,000 ways to choose the first word, and then you have 10,000 minus 1 ways to choose the second one. Now most of these combinations would they already paint themselves in a corner that for the 2 words that there is no way to complete the rest of the square. So any search of this nature always lives and dies in realizing as quickly as possible that it has painted itself inevitably in the corner and turn back right away, instead of exploring all the 10,000 to the power of 3 ways potentially to try these words, and nothing works because the vertical words do not work. So we're gonna be needing a bit of cleverness here, so that the way that we're gonna be doing this is building up the square alternating horizontal and vertical words. So initially, what for example has happened here, now that I run it in REPL and printed the 6 word squares with a bit of like a ASCII lining, like it's a ADs again. So a word square build up starts with the first row, but then each level of recursion trying to complete the rest of the square always switches the direction. So the second level, knowing that the first row is urent, so then has to build the first column. So all the words that start with the U, and then so urent, so suppose trying unius, and like I said, so I don't know what most of these words mean, so I take the word of the word list composer that this all means something. And then so once we have chosen the first horizontal word urent and the first vertical word unius, the next level of recursion, so now it's so in the odd levels we look for a horizontal, and even levels look for a vertical. Then the second horizontal word therefore has to start with an N. So now we only go through words that start with an N. And you notice deeper in the recursion, once we have already set up like a 2 horizontal words and therefore 2 vertical words, the third horizontal word then has to be something that starts with the prefix it. So the number of potential words diminishes by order of magnitude at each level, and then has to be so when we try some other words that start with the it, I'm sure there's plenty of them, but then in the next level of recursion, the third column, so suppose it's something like a it x something, so then we realize that there is no word starting with x, and then that's a dead end right away. So then we turn back as soon as we realize that things are wrong. So let's take a look at the code from the word fill here. So the recursion, but this actually, so remember that the only thing that is needed to turn a function into a generator is using yield instead of return. So this, since we are yielding the results instead of returning them. So this is now a generator, and this is a recursive generator. Observe a sneak preview. We're gonna be yielding from another recursively created generator to generate the rest of the square. So let's read through this and see the idea how this works. So word fill, so parameters n, so is the size of the square. So the base case is that when the row number, remember row numbers start from 0, so then when once the row number is equal to n, so that means that we have already filled the n rows and without creating a crash in the vertical. So now we're gonna be just yielding the horizontal words. So we only yield the horizontal words because once you know those, so then the vertical words are determined. Well, we could also yield the vertical words, so then it's just the mirror, so the diagonal flipped version of the square. So horis, so this is the list of words, the horizontal words that have been chosen so far in the top level call. So when I equals 0, so nothing has been chosen, so horis is the empty list, and vert, so is the words that have been chosen to the first vertical rows. So we are, remember, building this word square alternating between rows and columns. And so first row 0 followed by next level column 0, followed by next level row 1, followed by next level column 1, and so on. Hoping that lots of pruning happens at each level so that every row is tightly constrained by the choices that we've done earlier. When you're searching, so then this being tightly constrained is a good thing, because if those constraints are something that you must obey, and this is in the problem that we must, so we might as well use those constraints to lighten our workload. We don't want to loop to the entire list of words. We just want to loop to the words that fit into our tight constraints. The less branching, the faster the solutions are gonna appear. The word list is gonna be the alphabetically sorted word list, so we can use the previous trick of binary search to quickly determine, find all the words that start with the given prefix. VV, a little recursion helper, I'm gonna explain it later. And this setting Babbage, so I read originally from this problem that the Charles Babbage liked it, so perhaps that's what inspired him to start on a computational machine, that he doesn't need to do this by hand. So let's just say that the Babbage is when all the horizontal and vertical words are the same. So making this parameter to be true, so then search is constrained to the squares where the horizontal and vertical words are the same. Now, the fact that this is a generator, it is still a recursive generator, and I'll never get tired of saying that every recursion always must start checking for the base case, so otherwise your recursion is stuck in an infinite regress. So the base case, once we have enough rows, so then we just yield the horizontal rows as the answer. Otherwise, so at this level of recursion, we're always filling the horizontal word. Well, how come at some levels we're not filling the vertical words like I just said? Because of a simple trick that in every recursive call, notice when we make a call, then so in the non-Babbage version, we simply exchange vertical and horizontal. Like every level of recursion conceptually flips the word list, the square diagonally. So then, if we are currently filling the horizontal words, then in the next level of recursion, because when we exchange the roles of the vertical and horizontal, so then when we are filling the horizontal words, then we are in fact unknowingly filling the vertical. So this kind of like a symmetry tricks often help in recursions. Otherwise we end up writing two identical functions, except that the horizon and vert have been interchanged, and whenever you're copy pasting and making some small change, so that's when you need to stop and think back, so what is the general non-repeating yourself way to say it. Okay, so now the task, remember, keep the eye on the price. loop through all the ways that are still legal ways to choose the ith horizontal word. So the ith horizontal word has to start with the prefix that we get from the vertical words that have already been chosen. So if the two first vertical rows have already been filled, so then the horizontal word has to start with the two characters taken from what character those vertical columns have in this particular row. So this is already a nice tight bound and keeps getting tighter the deeper we go. The same as before, so I use the bisection, the binary search, to find the position where the words with this prefix would start, if there exist any. So if there don't exist any, the while loop correctly does nothing at all, and this entire level then terminates and returns. So this same loop that we saw earlier, so as long as the current word is still starting with the same prefix, then so take the word, and if this then the rule was that you cannot use the same word twice, so the word cannot occur anywhere in the currently chosen horizontal or in the vertical. Well, this we don't need to use a set because these lists are so short that the in is immediate anyway. So if the word has not been chosen yet, so then take it as our current candidate for the next horizontal word. Remember this principle in the recursion that when you modify your data structures before the recursive call, then when the recursion returns, so then you have to undo the modification to restore your data structure to the state that it was before the recursive call. So for the purposes of the recursion, so let's try this word as the next one for the current row, and then the rule for the Babbage. So if it's a Babbage, so then we go up one level, but notice in the Babbage, so the two lists are always identical. So both the horizontal and the vertical words are the same. Whereas in this general version, then we exchange the role of the vertical and the horizontal, and then so now the trick, the VV here, the recursion depth increases only in every alternating level, because once we've chosen the horizontal word for the current level, so then we have to also choose the vertical word for the current level. So this VV is always either 0 or 1, so telling whether we are supposed to go to the next level in the recursive call, and then the flip-flop between 0 and 1. So if you say VV, new value is 1 minus VV, so then if it was 0 it becomes 1, and if it was 1 it becomes 0. So this VV in every alternating level is 0 and 1, so then therefore increasing the recursion depth at every alternating level. So we make one of the, so this is not a branching recursion here, because exactly one of this is executed. The branching comes in the loop, so as many words that there are starting with the given prefix, that's how much branching there's gonna be in the recursion. So initially, so it's just the way that it is. So then all the words start with the given letters, so there just is thousands of them. So then the recursion is gonna be branched sideways to the 1000 direction. This is not a problem for memory use, because this whole thing is lazy in a sense. It just tries one branch at a time. And the depth of the recursion, so of course cannot be more than 2 times n, so the depth is never gonna become too deep. So try the word and then yield. So notice we can get multiple solutions. There can be, and in general there will be more than one way to fill in the rest of the word square, and this will now systematically produce them all. This will explore the entire tree of possibilities. No stone is gonna be left unturned. Then just go to the next word, and once you processed, then there is nothing more to yield, just return to the previous level. So this lazy generator, if it ever reaches the end, that's how it knows that it's done, and it will shut down the shop in the controlled fashion. So this is kind of interesting to study. So combining the two powerful techniques, lazy sequences and recursion. So basically these lazy sequences are recursively created, then the results are combined to produce another lazy sequence. So here, so we can try this. So n equals 5 wasn't too long. I guess I could have had this running while I was yapping here. So let's just try. Let's try to find 1 6 letter word square in the end. So while it is running, so I can look at the rest of the logic. So remember, as I emphasized enthusiastically a moment ago, this generator produces all the solutions. But when you have a lazy sequence, now here we don't want all the solutions, so we're just slicing with 1. So from each of these potentially very large lazy sequences, so each one starting from a randomly chosen first word, so that we get some randomness, that we don't get the lexicographically first word square. Now that I think of it, that would be an interesting problem too. We could easily find it out. Their CHR and ORD, each other inverses. ORD turns character into a code point. CHR turns a code point into character. So notice the clever trick. I don't know if that's so clever, but the next character in the Unicode to the current character. So bisect right can be used to tell us exactly where to end. So we choose a random word from all the words starting with the given word list. Still haven't found a solution. This whole task is, again, this is exponential search for you. Just one, so at the inflection point. So the number of possibilities here, the massive branching grows exponentially. So this is gonna explore a lot of dead ends, painting itself in a corner before it finally finds one. So let's read the Wikipedia examples while we are waiting for result to come out. So here is a humongous, but this is again a Babbage word square. So so if you cannot use the same word in here, you can make up some different word, and now you have an exponential number of combinations. Order 10 square, or even not the Babbage one, so maybe one of my students will find one.